So Mike, when you're not thinking about ignorance, you actually have a day job that involves doing a lot of work with statistics, and so that's actually one of the areas of expertise that you have. And statistics is one of the disciplines that's really thought about uncertainty and has ways of dealing with it. Can you give us some insights into what statistics does and how it deals with the unknown?
Well, I can try. Statistics really predicates its framework on probability theory. And so a statistician will characterize the unknown in terms of chances, or probabilities. And they then try to model those probabilities in such a way as to be able to come up with estimates of how big the probabilities are for various events, to be able to predict which events are most likely to occur, those sorts of things. But it really is grounded in probability theory.
And how's that changed over time? Are there a set of laws there that have always worked, or has it evolved in some particular way?
Well, the basic laws have always worked. So if you go back to the middle 1600s, when probability theory is first elaborated by Pascal and Fermat, they work out pretty much the basic laws of probability. And those don't change. And in fact, by the time you get to Kolmogorov in the 1930s, where he beds it all down in very careful mathematical axioms, most statisticians would still use his axioms as the basis for probability. What has changed is the extent to which statisticians, at least some of them, believe probabilities can be applied to different kinds of events. So it used to be that people pretty much thought of probabilities in terms of long-run relative frequencies of events. So I take a coin that I think is fair, but I want to find out if it's fair. I toss it many times. I toss it 1,000 times, let's say. If it comes up heads about 50% of the time, then because I've tossed it so many times, I can be reasonably sure that probability of heads is 1/2. Where things have advanced considerably and where there are still some disputes now is in applying probabilities to unique events. Like, what's the probability that there will be nuclear war sometime in the next 10 years, let's say? Or what's the probability that I will get a heart attack before I turn 80? Those are unique events, and a strict relative frequency person would say, well, you can't pin a probability on those things because they're unique. Either they will happen or they won't. Mm-hmm. Let's go down to the racetrack, okay? So we've got a set of unique events. On this particular day, we're going to have a race. There are, say, 10 horses involved in the race, and I want to try to pick the winner. So I'm going to pick a horse whose probability of winning, I think, is the highest. Now, if I don't obey the laws of probability in assigning my intuitive numbers to the chance of each horse winning, then I might make those probabilities add up to more than 1, or I might make them add up to less than 1. Mm-hmm. And a smart bookie could get me into a situation where I'm actually sure to lose in my betting because I haven't made my probabilities add up to 1.
Right. So come back to the nuclear war example. How do you turn whether or not there might be a nuclear war, how do you turn that into a probability exercise?
Well, this is where some of the debates happen.
Right.
For some Bayesians, for example, they would say, well, you just you consider the factors that lead you to believe the extent to which it's likely that a nuclear war is going to happen sometime in the next 10 years, and you try to pin a number on that as best you can.
Oh,
so
okay.
So you might say, well, intuitively, I think maybe it's probability of 1/3 or something like that. And you can actually see examples where decision makers have done that. Mm-hmm. So in the John Fitzgerald Kennedy, former president of the United States, in assessing whether or not bringing the Russians, the Soviet leaders at the time, Khrushchev, to heel on putting nuclear missiles in Cuba would lead to nuclear warfare, apparently estimated that probability as about 1/4.
Right.
He bet on nuclear warfare. with a quarter probability, he bet against that. He said, I'm still going to force Khrushchev's hand, even though I think there's about a 25% chance that this could result in nuclear warfare.
So let me see if I understand that correctly. So if in the current day we're worried about, for example, terrorists having access to nuclear weapons, and so we'd figure out which are the main terrorist groups and what the chances are that they might have had access to the technology to make it, to the raw materials, and then you could put all those things together to come up with an estimate. Is that the sort of thing that we're talking about?
Yeah, an expert in terrorism might very well proceed that way, but they would still have to make some judgments. That would be based on their experience, their intuition, some of the intelligence that they're getting about how terrorist groups operate, the extent to which they have those sorts of resources available to them, and all those sorts of things.
So we've got this basic set of rules of probability. We've got some areas where you can apply them with a great deal of confidence, and now it's been pushed out into other areas, particularly single events, and thinking about those. Are there other ways in which statistics has evolved over time?
Quite a few. The variety of techniques and the power of the techniques that we have available now has advanced very, very considerably over the last couple of decades, partly because, in fact, perhaps even mainly because of the expansion in computing power that we have. It used to be that there were whole sections of statistical theory that you couldn't use because it required, first of all, it required computers.
Right.
Right. So it's humanly impossible to do this, some of these computations. You need a machine that can do it. And then secondly, if the machine is too slow, as the early computers were, if it's not powerful enough, if it doesn't have enough memory, then you still can't use those techniques. So now we've got a lot of computing power, and so that's meant that some of the techniques that used to be off limits, they were nice theories in academic papers, but nobody could use them. They're now off the shelf and we can use them.
You've also done a typology of unknowns, which we dealt with in Ignorance 1, and statistics, I don't want you to go through the whole typology again, but statistics is actually only a small part of that. So if we think about unknowns more broadly, there are whole swathes of unknowns that statistics just isn't relevant for. Do you want to just give a couple of examples of that?
Sure. Right down close to statistics and probability are concepts like vagueness or ambiguity. So as we talked about in Ignorance 1, if somebody says this food is hot and says nothing more, then I don't know whether they mean it's high temperature or spicy, or stolen, sexy, or any of those things. And without knowing that, it becomes quite difficult to do any statistics with lots of people saying the food is hot, because I don't know if all those statements belong in one category or if they belong in separate categories, and if so, which categories they belong to. The same thing with vagueness. If somebody says, let's say I'm collecting information from people about how many times they visited the doctor in the last 2 years. Most of us have imperfect memory. Some of us may remember exactly how many times we visited the doctor. So I might get somebody saying, I visited the doctor 7 times in the last 2 years. But somebody else might say, I think I visited the doctor somewhere around 3 or 4 or 5 times. And somebody else might say, several. I visited the doctor several times. What am I going to do with those numbers, right? They're all numbers, but a couple of them are vague. And so then I have to figure out, what does several mean? Or even if somebody gives me an interval, like, somewhere between 3 and 5, do I take the midpoint? How do I work with that statistically? And so there are debates about the best ways to treat vagueness, ambiguity, those sorts of things in statistical analysis.
There's been quite a lot of concern about the statistical literacy of the general population. Why is it important?
Well, one reason is that a lot of material is being presented to us in the popular media and by policymakers and lawmakers that have statistical components to them. So, for example, if you serve on a jury, you might be given statistical information about, say, DNA. The prosecutor might be telling you there's a 1 in several million chance that this DNA does not belong to the defendant, and blah, blah, blah. Do we really understand what a probability like that means? There's a lot of evidence that says we don't really. In fact, there's a lot of evidence that says that most of us can't really distinguish 1 in 1,000 from 1 in a million, despite the fact that those are really quite different. Another problem, of course, is that there are plenty of people who would like to take advantage of us and persuade us to buy things and or to get money from us and so on and so forth, or to get us to vote for them by bamboozling us with numbers. And so it would help if a citizen, if they want to be an eligible voter or consumer, to have at least a basic idea of some of the ways in which they can be lied to and how to know when that's being done to them. And then the third thing is that being able to, in a sense at least, do some basic analyses of your own data, because a lot of us now have a lot of data available to us, can help us get some ideas about some things that are important to us. These days you can monitor many aspects of your health. For example, I know plenty of people who regularly take their own blood pressure, monitor their own heart rates, these sorts of things. So they're keeping tabs on their health by gathering numerical data. Now, one of the problems that they have is that their blood pressure, let's say, can vary a lot. It would be good if they had some idea about when they should regard that variability as problematic, symptomatic that something's really going wrong, as opposed to being just normal variability. Your blood pressure does go up and down throughout the day, depending upon whom you're talking to and what mood you're in and all that kind of thing, as opposed to when something really pathological is going on.
Right. Can we just go back to the second example? So give us some examples about how statistics are misused, or how we can get an impression that something's really important when it's not. And one example is, you can be told that the crime rate's gone up by 200%, but in fact, if you look at the numbers, it's gone from 1 to 2 or whatever it's gone to. Can you give us other examples of that?
Sure. Just about every day in the newspaper, in the financial section, you'll see a graph of what the stock market has done, say the ASX or the Dow Jones or something like that. And typically, the graph's axes will be cut and truncated in such a way as to make the variability look really big.
Right.
And so you can make a rise or decline in the Dow Jones or any other stock index look really dramatic by just cutting the axes so that the graph, the trend, fills up that space.
Yep.
But in fact, if you expanded the scale to include more of the scale for the stock, say the degree to which it's varied over the last year, then that decline might be this little tiny thing.
Right.
But our visual sense immediately gives us an impression that this truncated graph has got this big decline, let's say, and we go, oh, wow, stock's really come down. It's not until you drill into it that you realize it lost 2 points. So just being able to know things like, even basic things like that, can really help.
Right. The problem that I had when I was learning statistics was that at that time I was learning science, other science, which was all about truth. And the challenge that I had was that statistics wasn't about truth. It was about dealing with fuzziness, if you like, around the edges. And that transition was incredibly difficult for me to make, because I kept saying, so why don't you know why isn't it the same as physics? Why can't we? In fact, physics isn't as straightforward as it was when you taught it in first year. But that was a real dilemma for me. Can you say a little bit more about that?
Yeah, I think that's actually a major conceptual barrier for a lot of us. My background undergraduate degree was mathematics with a minor in physics. And initially I encountered the same issue. Most of the rest of mathematics is all about certainty. And the contrast between that and what goes on in probability theory and statistics is really quite marked. And many times I saw fellow students who were helping me in one math class. I was helping them in probability.
Right.
And that was partly because of that, that kind of barrier that you're talking about. I also saw some students, including myself, who got really, really fascinated by the idea that you could have a mathematical framework for dealing with an unknown like that.
Right.
I'd never run across anything like that in my life. When I was an undergraduate, I thought, wow, this is really interesting. I never dreamed that you could take uncertainty and turn it into mathematics of any kind.
Right. Well, Mike, that's been great. Thanks.